National Center for Theoretical Sciences of the TIFR. It is my great pleasure to welcome you all to this evening's public lecture by Professor Benedict Gross of Harvard University. ICTS is a newly established center of the TIFR with a very wide mandate, and one of its core mandates is engagement with the general public, explaining what we do in the broad scientific community. This evening's public lecture is a part of that engagement. I would like to invite the director TIFR now to say a few words.
Thanks, Avinash. And well, on behalf of the full community of the Institute of TIFR and its centers, it's my pleasure to welcome all of you to this public lecture this evening. As Avinash said, the ICTS, which is one of the youngest centers of TIFR, has been arranging public lectures as a part of its outreach activities. But actually, I would say for the Institute as a whole, we do take outreach rather seriously, and public lectures is one of the, major vehicles of our communicating to the public. And I guess the aim of this is to, communicate the excitement and the intellectual process of science, mathematics, whatever, to the public through the people who actually do it themselves, do research themselves. So with these few words, I'd like to say I'm very happy that Professor Benedict Gross from Harvard is here today, and we'll soon be talking about cubic equations. All right, and I have to do something?
I would like to request Professor Barma now to give a token of our appreciation to Professor Gross, a bouquet and let me also make an announcement. The next public lecture will be by Professor Terence Tao next month on 23rd of February. Now let me request Professor Prasad to introduce the speaker before the lecture begins.
Maybe I will request people standing to come here. I think there are many seats here, so there will be other people coming, so they perhaps will stand there then. All right, I'm very pleased and honored to say a few words of introduction for my teacher, Professor Benedict Gross from Harvard University. One should say that for a mathematical audience, he needs no introduction. In fact, I should say that today, we have been having this international conference for last few days, and I was just counting that out of the 5 lectures today, his name came up in a major way in 3 of the lectures in quite different contexts. So he certainly needs no introduction for the mathematical community, but for the public at large, I guess one needs to say a few words for him. So Professor Benedict Gross is a chaired professor at Harvard. He has done most of his career at Harvard, undergraduate, graduate, then he came back as the faculty there. So he got his PhD in 1978 under the guidance of John Tate, and he came back to Harvard as a full professor in 1985, where he served as the chair of the mathematics department, and then he became the dean of Harvard College, something which mathematicians rarely do, and I understand he did a great job of it, and he was still available in the department, and Okay, so Professor Gross has, in his career, received many honors and awards. He was honored with a MacArthur Fellowship in 1986, the Cole Prize of the American Mathematical Society in 87. He was elected to membership of the National Academy of US in 2004. Benedict Gross has had many students, and several are here. So it's our great pleasure and honor to have you here.
Okay, very good. Thank you. So I want to emphasize, first I want to thank the Institute for its invitation and to Pendra for that very kind introduction and for organizing a wonderful conference we've been enjoying. With respect to the conference, I want to emphasize that this is a public lecture. So I'm not speaking to the mathematicians at the conference who may find it a little strange, but I hope that the people who are in the public who've come to this lecture will enjoy it. And I also want to thank William Stein, who is a mathematician at University of Washington, and he collaborated with me on preparing the slides for this talk, and in fact he just gave the talk almost simultaneously at the meeting of the American Mathematical Society in Boston. The people in the back, there are plenty of seats up front if you want to come and sit down. So I'm going to speak about cubic equations. To mathematicians they're called elliptic curves. So there are really two types of equations in mathematics, and when you decide what field in mathematics you're going into, you choose your type of equation. So one type of equations are called algebraic equations. They're relations between quantities that involve the powers of quantities. So one of the most famous algebraic equations is the one that gives the relationship of the sides lengths of a right triangle. And in the West, this is usually attributed to Pythagoras, and who was a mathematician in the classical school of Greece. His approximate dates were about 600 years before our common era. Here's a bust of Pythagoras. Now, you shouldn't take this too seriously because this bust is completely imaginary and nobody has the slightest idea what Pythagoras looked like. And moreover, we're not even certain that anyone who was named Pythagoras exactly even existed. André Weil, who we'll meet later in the talk, who's quite a historian of mathematics, says that he has the same position in Greek mythology as Prometheus. In any case, Pythagoras didn't discover this wonderful theorem, one of the most beautiful theorems in the basis of Euclidean geometry, because it also appears in a sutra about Hayana 200 years earlier. These sutras are beautiful things. At the time when people did mathematics, they combined it with music and poetry, and so these things are expressed in rather poetic form. And we're going to see that even, even on the subcontinent, this theorem may have come all the way from Mesopotamia, where it was known several hundred years earlier. Well, that's algebraic equations. And the other type of equations in mathematics that one spends a lot of time with, and they're closer to phenomena in the real world, are differential equations, which relate in some way a derivative or several derivatives of a function to the function itself. The most famous differential equation is the one I've put up here, which says that the function whose derivative is exactly equal to the function. So its rate of change is the same as its value at that time. And to tell what that function is, you have to say where you're starting. So if you started at the time t equals 0 to have a value, a unit value, then we know that the only solution of this differential equation is the exponential function. And people in analysis like to expand functions in infinite polynomials that are called series or Taylor series. And the leading terms of the exponential function start in this way. And the exponential function governs growth in all types of situations. So in biology and physics, this comes up again and again. And the mathematical theorem is that any function that satisfies that differential equation with that initial value is the exponential function. So here's an occurrence of the exponential function in a local setting. This is the graph of the population of India. And It's experienced exponential growth in the last 50 years where there's been an adequate food supply. It's more than doubled since 1950. You can see a terrible decline here. That was during partition. Of course, when you spend some time in Mumbai, you realize that no one has the slightest idea what the population of India is. How would we ever count it? Okay, well, let's go back to algebraic equations. Let's go back to algebraic equations. So we'll return to this equation of the side lengths of a triangle. And what interested the classical mathematicians was that this equation had solutions not just in real numbers, which are what we use to measure lengths of the sides, but also in integers, in whole numbers. So the most famous, which people usually know, is the pair 3, 4, 5. A solution is sometimes called in mathematics a Pythagorean triple, a solution of this equation in integers. So A, B, and C integers such that the squares of the first two add up to the square of the third. So here are the first three solutions. And in this case, this equation has an infinite number of solutions. And there are many more solutions that are tabulated on a Babylonian tablet, which is almost 4,000 years old and sits in the antiquities of Columbia University. And here's the tablet. It's almost the same size as this slide. It's not much larger. And it tabulates the following Pythagorean triples. I mean, not just 3, 4, 5, and 5, 12, 13, but to quite large A, B, and C. And this tablet was deciphered by the great mathematical historian Otto Neugebauer, who felt that based on this and other remnants that we have of their civilization, in Mesopotamia at this time, they had a mathematics that was almost as advanced as early Renaissance Europe. Really remarkable. So I want to show you how it might have been possible for the person who inscribed the numbers on this tablet to have obtained all these solutions. It's very unlikely they just did it by trial and error. You don't just keep choosing numbers and summing their squares and seeing if it's a square. So let me show you how you systematically can find the most general solution to this equation in integers. Well, the first thing you do is you replace the integers a, b, and c by a pair of rational numbers. Those are quotients of two integers. And if a and b and c satisfy the original equation, then the rational numbers x and y satisfy this equation. X squared plus y squared is 1, which means that x and y are a point on the unit circle. Right? There's this blue is supposed to be the graph of all solutions x squared plus y squared is equal to 1. Of course, those are the solutions where x and y are real numbers. And we're supposed to find the solution where x and y are rational numbers, because then we can write them as a over c and b over c, and then a, b, and c will satisfy our original equation. So if we could find all the pairs x and y that were rational numbers that were on this curve, we would have found the general solution of the Pythagorean equation. So how do you do that? Well, you connect, for every point on the circle, you can draw the line that connects that point to this point on the circle, which has coordinates -1, 0. And that line will cross the y-axis at some point 0 and t. Now, it's clear from the fact that 2 points determine a line that once I tell you what x and y are, you can solve for this point t. And also, if I tell you what t is and what this point is, and we know what that point is, we can figure out what the point is of x, y, of intersection with the circle. And when you do the algebra involved in that, you find the following formula. That t is the quotient of y by 1 plus x. That's the slope of the line. And that x and y are a little bit more complicated, but in terms of t, they're given by these two formulae. Now, what's good about this is the following. If x and y are both rational numbers of the form quotients of integers, then it's clear that t is also a rational number. But conversely, if t is a rational number, so is t squared, so are these combinations of t squared, so is this combination. So if t is a rational number, so are both x and y. And this gives a way of enumerating the rational points on the circle by simply enumerating the rational numbers which lie on this line. And that's how you get to the general solution. So if we write a rational point on that line as p over q and figure out what x and y are, they look like this form. And then we clear the denominators because we really want to find the numbers a, b, and c. We find that a is of the form q squared minus p squared, b is 2pq, and c is q squared plus p squared. And this is the general solution of the Pythagorean equation. You choose two numbers, p and q, which are put in the numerator and denominator of this fraction. You define a this way, b this way, and c this way, and you found the general solution. So for example, the first three solutions, if you take t to be a half, you find the one that everyone knows, 3, 4, 5. You take t to be 2/3, 5, 12, and 13. T to be 3/4, 7, 24, and 25. And you can find all the solutions on that Mesopotamian tablet by taking different values of p and q. So this is an equation which has an infinite number of integer solutions and for which we know how to enumerate all of them. That's going to be the model that we'll discuss today. So this equation, the Pythagorean triple, let's see if I can go back, a squared plus b squared plus c squared is what we call a quadratic equation because the terms in the equation appear to exponent 2. You all know the quadratic formula. And the quadratic equations were classified by the classical mathematicians of Greece in terms of circles, ellipses, parabolas, hyperbolas. But this talk is about cubic equations, so let's go to that. So a cubic equation is an equation in x and y where one of the terms at least appears to degree 3. And you might wonder what's so special about that. Well, that's my job to tell you. But the most famous of the cubic equations was studied by Fermat. And he showed that, and let's see, maybe I have a picture of Fermat here. Let's see. Oh, there he is. Now, Fermat was a mathematician who lived in 17th century France. He was a magistrate in Toulouse. There's no evidence that he ever went more than 40 miles away from Toulouse. And he pursued mathematics as an avocation. At the time, there were really no professional mathematicians, but he's the person who really created the modern theory of cubic equations and also many of the modern techniques in number theory. We actually do know what he looks like because he was painted in his time. He was quite famous in his time. And he studied initially this cubic equation, and he showed that unlike the one we did with quadratics, where x squared plus y squared is equal to 1, which had an infinite number of solutions, this equation had only two solutions, namely the solution where x was 0 and y was 1, and the solution where x was 1 and y was 0. That's a very famous result of Fermat. We don't have his proof, but it's certain that he must have had a proof. It was reproved in the next generation by the Swiss mathematician Euler. And that's an example of a cubic equation that has only finitely many rational solutions. In fact, only 2. Whereas this cubic equation, which you can think of as integers, y squared plus y is y times y plus 1. So it's the product of two consecutive numbers. X cubed minus x is x times x minus 1 times x plus 1. So that's the product of 3 consecutive numbers. So this would say, when do you have product of two integers which are consecutive equal to the product of 3 consecutive integers? But you could also ask for solutions in the rational numbers. And this equation we're going to see has an infinite number of rational solutions, x and y. And so unlike quadratic equations, where once you find one, you can find an infinite number by the method I showed you, for cubic equations, you have to have some technique to decide whether you have a finite number or an infinite number of solutions, and that's occupied mathematicians since the time of Fermat. So now I'm going to try to show you what's so special about cubic equations, why they're the most interesting of all equations in two variables. So here's the graph that I've drawn of this equation that I said had an infinite number of solutions. And let's intersect this graph with a line, like we did for the quadratic equation. There it is. Now, the difference between cubic equations and quadratic equations is in the case of quadratic equations, the line intersected the circle in 2 points. But for a cubic equation, the line will intersect it in 3 points. Now, not all lines meet it in 3 points because this is the real numbers, but most lines will. And that's because the equation, oops, sorry, let's go back. We're getting way ahead of myself here. The equation of a line just says that y is a multiple of x plus a constant. And if you substitute that into this equation, you get a cubic equation in x, and that will have 3 roots, and once you find that root, you can figure out the root of y from the equation of the line. Now, what's nice about having a line that meets the graph in 3 points, and here are the 3 points in this case. The first point is minus 1, 0. The second point is 0, minus 1. The third point is 2, minus 3. Is that if you found 2 solutions of the equation, you could take the line through that point and find a third. See, you can't do that for a quadratic equation. You could take the line through 1 point and maybe find another one, but that 1 point doesn't determine a line, where 2 solutions determine a line. And in a cubic equation, that line finds 1 more solution. If you had a quartic equation or higher degree equation, that line would meet the curve in several points, and you wouldn't know what they were. But in cubic equations, if these 2 points are rational solutions, and here they are rational numbers, in fact they're integers, then the third point of intersection always turns out to be a rational solution. That's not difficult to show. And so it gives a process, once you generate a few rational solutions, for seeing if you can find any more. And by the way, you don't have to even find 2 solutions. You can take the degeneration. You see, if you take this line between 2 solutions that I've drawn here, and you let the 2 solutions become closer and closer to each other, the limit of that secant line is what we call a tangent line. So here we have just this one solution, but I've taken the line that's tangent to that point, and that meets the curve in one other point, and I find another solution. So this was a method that Fermat discovered, and it was a way he had of generating more and more solutions to equations, and the solutions frequently become quite large in this process. So for example, here I start with these 2 very simple solutions of this cubic equation. And I start to do this process where I take the line between the 2 points and I get another one, or I take the tangent line and I get another one. And I start producing more and more solutions to this equation, and you can see as the rational numbers are getting larger and larger. In fact, this is the last integer solution of the equation. So the last case where the product of 2 consecutive integers is the product of 3 consecutive integers is when you take 5, 6, 7, that's the same as 14 times 15, I hope. Yeah, I think that's right. And it's a little bit more work to show this equation. In fact, this process goes on forever. The solutions keep getting larger and larger when you take the tangent line. And this has an infinite number of solutions and only a finite number of integer solutions. Now, that might give you the idea that you can find solutions by finding some small solutions and then applying this process. But as we've learned more and more about these equations, we've learned that sometimes there are an infinite number of solutions, but the first solution is enormous. So you don't know whether there are infinite number of solutions until you found the first one. So here's an equation. It's true the coefficients are large, but they're not that large. And the first solution, the x-coordinate, has a numerator which has over 5,000 digits. Here it is. You can't actually see it. And here's its denominator. Now, you might wonder, how did anyone find that solution? Because you can't find it by just looking around. I mean, there would be too many numbers to try before you actually found. This is just the x-coordinate, by the way. The y-coordinate is bigger. The y-coordinate I can't print out on the slide. So part of the talk, I'll try to give you an idea of how people have been able to search for and find these enormous solutions on the computer. And that's part of the excitement of working on these equations nowadays, is it's so much interaction with computation. Well, let me get to the first important invariant of a cubic equation, which is called the rank. Now, for the mathematicians in the audience, I hope it's okay if I say that the solutions on these cubic equations have the structure of an abelian group, and the rank is the rank of that finitely generated abelian group. But because not everyone here knows what a group is, or what the finitely generated group is, I'll tell you that the rank is essentially the number of independent solutions that you need to produce all of them via this chord and tangent process. So for this equation that I previously wrote down, it turns out that the rank is 1. So once you found this solution, you can find all of them by that geometric process. But that's not always the case. But to give a little bit more flesh around this definition, if the rank is 0, that means there are only finitely many solutions. Like for the Fermat equation, x cubed plus y cubed is 1. And if the rank is positive, that means there are infinitely many solutions. And when the rank gets bigger, 1, 2, 3, that means there are even more solutions. And for example, if you want an example of an equation which you have different ranks, you just take this equation that I wrote down before, but instead of taking a to be 1, which is the y squared plus y is x cubed minus x, you take a to be 0, 1, 2, 4, and 16, and it turns out that the different cubic equations have rank 1, 2, 3, and 4. So you can produce equations of these ranks. Now, the big theorem is that the rank is finite, namely that there aren't too many rational solutions, that namely, after you found a finite number of them, you can produce all of them. And that's one of the great theorems in the subject, and that was proved by Louis Mordell, who I've pictured here, almost exactly 100 years ago. So Louis Mordell was a very proper British mathematician, but he was actually born in Philadelphia of Lithuanian immigrant parents. And the mathematician here was known to all the mathematicians here as one of the great mathematicians of the 20th century and perhaps of all time, and that's André Weil. And he, in his PhD thesis in the 20s, generalized Mordell's theorem in a slightly larger context. It's now usually known as the Mordell-Weil theorem. And that's the fundamental theorem of the subject, that there are only finitely many solutions over the rational numbers that you have to find before you can generate all of them. But we don't know if the rank can be arbitrarily large. The previous slide, I gave you examples of curves of rank 0, 1, 2, 3, and 4. And their coefficients are pretty small. But to look for curves which have larger and larger and larger ranks has been an interesting problem in computational number theory. And the current record is held by my colleague at Harvard, Noam Elkies, who I've pictured here. Noam is also a very talented musician. He's there at the piano. And he found an equation where the rank is 28. Now here the coefficients are quite large, as you can see. And these are the points, the 28 points that you have to find. They all have integer coefficients, amazingly enough. And from those 28 points, you can probably generate all the rest. And we don't know if there's an equation where the rank is bigger than 28. Some people think there is, some people think there isn't. We just don't know. In any case, people have been looking for some time, and Noam's record still stands. So I'm going to tell you about the major conjecture in the subject. The conjecture is something that mathematicians feel they have evidence for, but haven't yet proved, that was formulated by Bryan, Birch, and Peter Swinnerton-Dyer almost 50 years ago. So here's a nice picture of Birch and Swinnerton. That's Birch, that's Swinnerton-Dyer. It was taken on Birch's wedding day. So Swinnerton-Dyer was his best man. The English don't always dress this way. But it's quite a formal wedding. They were out in the garden, I think probably at one of the Oxford colleges. And I put it in here to show that people who do mathematical collaboration, and these two work together quite some time on these cubic equations, frequently become the best of friends. And you might think perhaps that's because there's no one else for them to talk to. And they made a wonderful conjecture which gave a prediction. If you looked at a cubic equation, it gave a prediction for the rank, the number of solutions, in terms of the average number of solutions that you would find at prime numbers p. So to tell you a little bit about that, I have to introduce the people in the audience who aren't mathematical background to the study of prime numbers, which is also a huge area in the subject of number theory. So a prime number is a number that's bigger than 1, not divisible by any smaller number. So the first few prime numbers are 3, 2, 3. 4 is not a prime because it's divisible by 2. 5 is a prime. 6 is not a prime because it's divisible by 2 and 3, etc. And the prime numbers start out. These are the primes, first few. And one of the great theorems in Euclid is that there are infinitely many primes. This list never comes to an end. There's always a larger element on this list. And it's become quite a challenge for computational number theorists to find explicit large primes because we don't have a recipe for generating the next prime. This is a very, the proof that there are infinitely many primes is extremely non-explicit. It's a proof by contradiction. And so this is the largest prime number that we know. And it's written in exponential notation. If you wrote it down, it would have 12 million digits, over 12 million digits. I'll try to give you an idea of how large that is in a minute. And on the other hand, even though we don't know how to write down the next prime, people have found experimentally, and this was done back in the 18th century, that the primes grow, the number of numbers less than x, here we're going all the way up to 500, there are about 85 primes less than 500. The rate of growth of the number of primes seemed to grow at a very regular manner. And that was a precise conjecture was made by Gauss, and it was proved at the end of the 19th century, called the prime number theorem. To give you a large prime, here's an example of a prime that has about 3,000 digits in it. Okay, that I could put on a screen. Now, if you want to imagine what this prime number looks like, okay, that's 12 million digits. Take this poor prime with 3,000 digits and replace each digit by the whole prime number. And then you get some prime which has about the right size. I participated in an art exhibit in Paris last year where a wonderful Japanese artist printed out a prime number of 7 million digits. So that's smaller than the largest one known. And the printout went about like this. It went from this wall to that wall. It was on a piece of paper that was about this big. And the digits were 5 pixels high and 3 pixels wide. So to actually read it, you needed a magnifying glass. And that's, of course, not the largest prime. There are infinitely many primes beyond that point. But that's the largest one that we found. Let's see if I can go on here. All right, and I want to say a word about primality testing. How do we know that a number like this is a prime number? How could you can't possibly check the numbers less than it and see whether it divides it. Well, there's some very clever methods. And it turns out that you can very quickly check if a number is a prime, almost in the amount of time that it takes down to write the number down. That's called polynomial time. And this was established in a famous paper. It's called Primes is in P. P means the things that can be computed in polynomial time. And that was now called the AKS algorithm after Agrawal, Kayal, and Saxena. Agrawal is a professor at the IIT in Kanpur. And I gather that these other two authors on the paper were his undergraduate students. So this was a huge breakthrough in primality theory. And it gives an idea of what undergraduates at IITs are like nowadays. I think we have to compete more, get them at Harvard, actually. Now, on the other hand, if a number fails to pass this primality test of AKS, namely you put the number in, it says yes or no. If it says no, that means in Euclid that it's a product of lower numbers and a product of primes. But to try to find those primes turns out to be a much more difficult process. That doesn't seem to be in P. It doesn't seem to be possible to factor numbers in polynomial time, although nobody can prove that. And that's the basis of almost all the public key crypto systems that are used nowadays. So anytime you send your credit card over the internet, it's usually encrypted using some algorithm that finds primes very quickly and then doesn't let you factor them. So for example, here's an example of a famous factorization that just occurred. RSA is Ravesh, Shamir, Edelman. They were the trio who were the most famous in primality testing before AKS. And they formed a company which guarantees security of electronic transactions based on this. And they put out some challenge numbers. So here's a number of, I think, only about 232 digits, which is not prime. In fact, it's the product of two prime numbers, each of which have 116 digits. And it was only recently factored. And this is about the size of the largest number that we can factor, whereas we can test primality for numbers that are billions of times larger than that. So that's an interesting application of number theory that it's able to create these kind of trapdoor codes. OK, enough on primes. Let's go back to the problem that Birch and Swinnerton-Dyer treated, which is to study cubic equations by looking at them in the prime number p. Now, what do we mean by that? Well, what you mean is, let's go to our favorite cubic equation, the y squared plus y is x cubed minus x. And now you don't look for exact solutions, but you look for solutions x and y, which are numbers, integers, such that this side has the same remainder as this side when divided by p. So you can divide by a number, you can take its remainder. So for example, if you take x equals 3, this side becomes 27 minus 3, which is 24. You take y equal 1, this side becomes 2. Now 24 is not equal to 2. So this is not a solution of the equation. But it is a solution at the prime p equal 11, because 24 and 2 give the same remainder when you divide by 11. And this is a type of equivalence on solutions when you look at them up to their remainder. And it turns out that that this side gives the same remainder as this side depends only on what the remainders of x and y are. And there are only p possible remainders for x, between 0 and p minus 1, where p is your prime. And there are only p possible remainders for y. So the number of numbers you have to test to see whether this gives a solution up to remainders at p is just p squared numbers. And people do that. So here for this equation, there are only finitely many solutions because they're a subset of this p squared solutions. And here I've marked out the solutions for this equation. If you take p equal 23, there are 23 possible values of x. There are 23 possible values of y. And I've put a blue dot at the pairs where they solve this equation at the prime 23. And it turns out there are 22 solutions. And here's a little bit more complicated box at the prime 71. There are 71 values of x to check. There are 71 values of y to check. And of those 71 squared values, exactly 63 solve this equation up to remainders. So each equation that you have, for every prime number p, you could count the number of solutions of this equation. Now notice that if you had an actual solution of the equation, so you had x and y that actually solved this equation, then it would give a solution for all primes p. And if you had many different solutions of this equation, so the rank was large, you'd get many solutions for the different primes p. And it's common to write the number of solutions in this form as a deviation from p plus 1, and to define a function of one variable. And this, all at once we get back into the world of differential equations and analysis, that encodes all the information about the number of solutions at a prime p for every prime p as an infinite product. Remember, the number of primes is infinite. And if you make this product, you can gather terms, and you get a series that looks like this, which is an infinite series. And you think of that as a function of the variable s. And this function that people define simply encodes how many solutions there are of your fixed equation at every prime p. And I should say this definition only works in a small region where you have to take the variable s to be bigger than 3/2, where the product converges. And if you try to look at this function in some region beyond where s is bigger than 3/2, you have no idea what its value is at all. No idea. You can only define this whenever this product converges. And for what we know about this number of solutions at a prime p, we know this product converges for large s. However, Birch and Swinnerton-Dyer had the wonderful idea to see what happens when you just set s equal to 1. Now notice that 1 is over here where we can't evaluate this product. So everything we're doing now is illegal. But you get quite far in mathematics by trying things that are illegal and then trying to justify them. So we're going to formally set s equal to 1 in this product. And remember, this product was given in this form. So we just take s and we set it equal to 1, and we get this product, ap times p inverse plus p inverse inverse. And when you work that out and you clear the denominators, you get the product over all primes p of p divided by the number of points at p. Now, remember the principle that the more points we had over the rational numbers, the more points we'd expect at p. And so if we had a large rank, we'd expect that AP was in general bigger than P. And so we'd be making a product of numbers that were less than 1. And that would go to 0. So if it's large on average compared to the prime, that this product will approach 0. And the larger it is, the faster it'll approach 0. To give you an idea how fast it does approach 0 in some cases, I calculated this function, and this is its value for p less than 50, for p less than 100, for p less than 200, for p less than 300, etc. For the cubic equation that my colleague Nomelkis found that has rank 28. Now you might say, how could you do that? The coefficients were so large. But all you need to store is the coefficients, what their remainder is when you divide them by p. And that's just as good for large coefficients as for small coefficients. So when you take the product, you see that it goes to 0 rather quickly because on average this number is much larger than the prime p. So here's what Birch and Swinnerton-Dyer actually made as a mathematical statement. After doing a lot of computation and a lot of experimentation, they proposed the following. First of all, this infinite product, which we only had defined for real part for s bigger than 3/2, has a way, there's a natural way to continue it to some region containing the point 1. So that you can actually talk about evaluating the function at 1 instead of just making an infinite product. And the second was, and this is wonderful, that the function should behave analytically near 1. So it should have a power series, a Taylor series. And the order of vanishing of that function should be the rank of the cubic equation. So the more points, the faster it goes to 0. So that would say if the rank is 1, the function vanishes. If the rank is 2, not just the function vanishes, but its derivative vanishes. If the rank is 3, the second derivative should vanish. And then they actually made a conjecture for the leading term in this power series expansion at 1 in terms of some invariance of the cubic equation. That's not what we're going to do today, but this is the full conjecture of Birch and Swinnerton-Dyer, and this is considered one of the great problems of number theory today. It's still open after 50 years, and the Clay Institute, which sponsors a lot of mathematics, has offered a prize of $1 million to whoever ever solves it. Of course, no one would solve it for that reason. Now, the most mysterious arithmetic invariant was studied by John Tate and Igor Shafarevich. Here's a picture of John Tate, my teacher, over here, and Igor Shafarevich, great Russian mathematician. And they studied this question at about the same time in the late 50s and early 60s, and they conjectured that this mysterious invariant was finite. And Tate, who wanted to put this conjecture on Shafarevich, called the invariant Sha, the Cyrillic letter, which is the beginning of Shafarevich's name. And so this leading term involves the number of elements in this Sha, which we don't even know is finite. So Tate liked to describe this as a conjecture about a function where we didn't know it was even defined in terms of an object that we didn't even know was finite. However, there was a lot of computational evidence in favor of this. Okay. Now, let me tell you what an analytic continuation is in some terms for those people who are concerned about that. You see, very frequently you're given a function by an infinite series or an infinite product. Like this famous geometric series, powers of x, converges as long as x is between -1 and 1. But you can't put a larger value of x in or a smaller value of x in. However, in that region, the function is equal to 1 over 1 minus x. And that function extends to a larger region. So here's the graph of x to the n between -1 and 1. But if it's equal to this function, you can define this function for all x less than -1. And here's how it continues. You can't define it in this region because it has a pole at x equal 1. So that's what Birch and Swinnerton-Dyer were hoping, that this infinite product expansion that they gave for the L function would have some continuation. And that continuation was proved recently in '95. And it was proved by Andrew Wiles and Richard Taylor. And they proved more. They proved that the infinite series that you got by replacing this n to the minus s by an exponential function was something called a modular form. And here they are. This was the critical result, the proof that this L series of an elliptic curve was related to a modular form. That was the critical result in the proof by Andrew Wiles of Fermat's last theorem, which is a generalization of Fermat's result that the equation x cubed plus y cubed is equal to 1 has only the solutions 0 and 1, to the equation x to the n plus y to the n is equal to 1. That also only has the trivial solutions. That had been conjectured by Fermat and was one of the most outstanding problems in mathematics. And people had shown that if you could prove that this was a modular form, you'd be very close to the proof of Fermat's last theorem, and that was Wiles' strategy for the proof. So that was the first step in the conjecture of Birch and Swinnerton-Dyer. Remember, there are really three things. There's the analytic continuation, so you can talk about the function at 1. There's the order of vanishing, so you get something where it's related to the rank. And then there's the leading term, and also the finiteness of this invariant SHA. So I worked on this problem in the early 1980s with mathematician Don Zagier, who now teaches in about 4 different places, but in particular is at the Max Planck Institute at Bonn and also at Collège de France. And we proved a limit formula for the L function, namely in the neighborhood of 1, we understood something about the behavior of the L function. And Victor Kolyvagin soon followed with some work on the group SHA of Tate and Shafarevich, and we can now prove the following result. This is what we know about the conjecture of Birch and Swinnerton-Dyer. First of all, if the L series is non-zero, and that makes sense because by the work of Richard Taylor and Andrew Wiles, we have the L function now defined at 1. If it's non-zero, the rank is 0. So that's what Birch and Swinnerton-Dyer predicted. There are only finitely many solutions. So that gives a criterion in terms just of the number of solutions at the primes p for deciding that there are finitely many solutions. And moreover, we could prove, and this was harder, that if the L function was 0, but the derivative was non-zero, so the order of vanishing was 1, then the rank was 1. That was also predicted by Birch and Swinnerton-Dyer, and there are infinitely many solutions. And in all of these cases, the proof came along with the fact that the Tate-Shafarevich group was a finite group. So in these 2 cases where the function either is non-zero or its derivative is non-zero, we pretty much have the entire conjecture. So here's a picture of Don Zagier about the time we did the work together. And here's a picture of Victor Kolyvagin. I should say that Zagier was a mathematical prodigy. And I met him when we were both the same age. And I was starting as a graduate student, and he was visiting Harvard as a professor. And this struck me as very unfair. But life is unfair. Kolyvagin was a student of Shafarevich at almost exactly the same time that I was a student of Tate's. And I think this illustrates that mathematics has a wonderful way of passing problems from one generation to the next. And Dipendra said, you know, I was mentioned in these talks today. I was mentioned because I couldn't do anything about the problem. I just left it as an open question, and then people solved it in the next generation. And that's a very satisfying thing to see happen. Okay. Now, on the other hand, we're in the situation today that when the order of vanishing is greater than 1, so if the function vanishes and its derivative vanishes, now that says the rank should be at least 2. So we should be easy to produce points, but we don't know how to do anything. We can't prove that SHA is finite. We can't prove that there are points, anything at all. But what people have done is to use the computer to do some very interesting experiments on this. So to give you an idea, for the first curve of rank 2, which is given by this very simple equation, we know that the order of vanishing of the L function is 2 by computation, and we know that most primes up to 50,000 don't divide the order of SHA. There's a very finite list of primes which we haven't been able to resolve, which possibly divide the order. And the conjecture predicts in this case, by the way, that the Tate-Shafarevich group of this curve is just got 1 element in it. So no prime should divide it, but we can check this up to about 50,000. And these computations have been done by mostly by my collaborator on this talk, who you can see flying off his skateboard here. That's William Stein. The younger generation of mathematics does these kind of stupid things. So as far as the computer tells us, everything is good with the Birch and Swinnerton-Dyer conjecture. But mathematicians, unlike other scientists, are not happy with this experimental evidence. I mean, if the Hadron Collider finds evidence of the Higgs field or the Higgs particle, the physicists will be delighted. But they'll never prove the existence of the Higgs particle. It could always be caused by something else. But we really want to prove the conjecture and understand why it's true. And all this computational evidence is really just very tantalizing. So now I want to talk about something that has almost nothing to do with the Birch and Swinnerton-Dyer conjecture, but is recent work of Manjul Bhargava, on the study of the rank of elliptic curves where you considered the average question, not the question for any given cubic equation, but for all cubic equations. It's a completely different approach. And this is, I think, a tremendous breakthrough, one of the great things that's been done in the subject in the last 25 years. And Manjul is here and at this conference, and if you want to hear more about this subject and go to a really beautiful lecture on it, I suggest you come to his lecture tomorrow morning. Beautiful speaker on this. And let me just try to summarize at the end of this talk what he's done with this problem. It's not related to the conjecture of Birch and Swinnerton-Dyer. It's a completely different method of attack, but it also uses analysis. What's amazing to me is that all of the methods to study this algebraic problem, which is just about algebraic equations, end up using techniques in analysis, namely techniques from differential equations, et cetera, infinite products, infinite series. Manjul uses methods from what's called the geometry of numbers. Okay, so there's a picture of Manjul. So let me give you an idea of what his method does. He first starts off by observing, and this is a very simple observation, but I don't think anyone had made it, is that you can put any cubic curve, oops, sorry, let's go back. Any cubic curve has an equation of this form, ax plus b, where a and b are integers, whole numbers, not divisible by the fourth power of the prime or the sixth power of prime for any prime p. That means a is not divisible by the fourth power and b is not divisible by the sixth power. Namely, you can change your coordinates x and y on the equation to get the same essential equation in this form. So that's very useful because it gives us a way of enumerating the different equations, which are cubic equations over the rational numbers. Namely, we define the height of this equation, e, as the maximum of these two integers, a cubed and b squared. You take their absolute value, so it's a positive number. And one of the, these are both positive integers, and you take the largest one. And then what's clear is that there are only finitely many curves where the height is less than x. Because you see, if a cubed is less than x and b squared is less than x, then there are only finitely many integers in that size. So on the other hand, as you let x go to infinity, you're getting all the curves. And let's call the number of curves which have height less than x, n of x. And it grows at about the same rate as the 5/6 power of x. Because if a cubed is less than x, that means a is less than x to the 1/3. So they're about x to the 1/3 values of a. And b squared is less than x. That says that b is less than x to the 1/2. So there are about that many values of b. And the product gives you about how many choices of these pairs a and b you can make. OK. Now, Manjul makes the definition of the average rank as you take the sum over the curves whose height is less than x. So this is a finite sum. And you put the rank of the curve, which is some number, 0, 1, 2, 3, etc. And you divide by the number of curves whose height is less than or equal to x. So that's like an average, right? I mean, and then you take the limit of that as x goes to infinity. So you're eventually summing over all cubic equations. But each term is defined for a finite number. And we suspect that the average of this rank should exist, and it should be equal to 1/2. That's a conjecture that was made by Dorian Goldfeld, who's also at this conference. And in fact, we suspect a lot more. We think that on average, half of the curves have rank 0, and half of them have rank 1. That doesn't mean that there are no curves of rank 2. It just means they're very sparse set, so they don't really appear when you take this average process. So if that were true, I'd be very happy, because then my results with Zagier and Kolyvagin would essentially prove the Birch and Swinnerton-Dyer conjecture on average, because we could do the rank 0 and 1 case. What we can't do is all the ranks bigger. So I'd be happy to take an average of $1 million. Now, methods of Bhargava have not yet been able to prove that the average rank is 1/2. But he and his student, Arul Shankar, have been able to show why there is an upper bound on this limit. You see, a priori, this limit could become arbitrarily large. Maybe as you keep looking at larger and larger equations, the rank gets larger and larger and the limit goes to infinity. But the first thing they were able to show is why there's any upper bound on the limit. And then, with a lot of work, they've obtained a specific upper bound, which is less than 1. So if they don't know yet that the limit exists, but if it exists, it's less than 1. So that's getting quite close to a half, and shows that on average, we're beginning to understand elliptic curves or cubic equations, even if we don't understand them for a given case. So I urge you to go to his talk tomorrow, where you can hear more about this. It's a wonderful new method that's been introduced into the subject. And so finally, I just want to say thank you. So this is a picture of me that was taken some 40 years ago. So I was a student. You can see I was very much into India at the time. I was a student in Chennai, and I was studying Carnatic violin. And I had some hope at the time of becoming a musician, but the talents of the musicians in Chennai convinced me that I should go in another direction. But I did see what a wonderful life they had in pursuit of a tradition that went back thousands of years, and they were intimately involved in it and creating new parts of it. And I feel the same is true of a life in mathematics, that you get to belong to a tradition that goes back to the fundamentals of human thought. The most basic thinkers of all time have thought about mathematics. The great thinkers have contributed to it. You can participate in a tradition. You can hope to make a little advance, and you can pass problems on to the next generation. So I hope you've gotten some idea of the excitement of working in this field. And I'll stop now, and I'll be happy to take questions.
There are any questions, maybe Professor DeGrosse could respond to them.
In the last slide, the conjecture limit, can computation help with that? Or?
No. In fact, that's a very interesting question. Before Bhargava and Shankar approved their results, the computations did not appear to show that the limit was going to be a half. Because you never know if you're computing far enough out to make that computation. It appeared from the computations that a positive percentage of cubic equations had rank 2, for example. And now we don't believe that at all, based on this. So it's always better to have some theoretical understanding of what's going on than just brute computation, because you never know in mathematics if you've computed far enough. Yes?
The slide of the points modulo P,
Yes.
fixing the symmetry.
Yes, that's very good. So that's a good, very good observation. Let me go back to that. That's a great observation. Here we are. There's a lot of symmetry in that slide. And that's because this equation is not quite y squared as this. But suppose you were to complete the square of this equation and turn it into y squared as a polynomial in x. Then every time you had a solution xy, you would also get a solution x minus y. And if you translate that in, you'll see that that causes the symmetry of this. So there is a certain beautiful symmetry around the axis here, and that's essentially y going to minus y.
All right, so if there are no more questions, let's thank the speaker.
There's some tea, coffee, and refreshments.
Well, high tea.